Hello and welcome back. We are discussing binary search trees. Just as a quick reminder from our previous video, we finished off discussing how we do searches and inserts in binary search trees. As a quick exercise, let's just draw the result of inserting the following values into our tree: 16, 17, and 23 in that order. The sort of exercise to the reader here is, does the order matter to your answer? The best way to test this, if you don't already know, is to try to insert them in different orders and see if it affects your tree. And what you will find is, yes, it does affect your tree. So 23 doesn't matter so much when you insert 23, because that's the only one of these three values that goes to this side. But because 16 and 17 both live to the right of 15, the order in which you enter these will change the structure of the tree slightly. So let's go ahead and walk through it in the order that is sort of stated, and then we can go from there just to sort of look at what it looks like otherwise. So if we start with 16 and we do our same insert pattern, we see that 16 does not equal 18, it is less than it, and that we can walk left, so we do. We see that 16 is greater than 12 and that we can walk right, so we do. We see that 16 is greater than 15. However, there is no child to the right, so we do our insert right here, and we have placed that node in its correct home. Next, let's look at 17, and 17 follows a mighty similar path, right? So it will do the exact same thing where it's less than 18 and goes this way, greater than 12, greater than 15. It comes across our brand new 16, and we know we're bigger than that and that there's nothing here. So we actually end up putting it right here. And we can see exactly why, if these were put in different order, putting 17 in first would potentially result in a different tree. If we put 17 in first, 17 would end up here and 16 would end up over here. So our tree would actually look quite different. All right. The last one we need to enter is 23. So I'll go ahead and add that brand new node right over there. 23 is greater than 18 and we go right. 23 is less than 27, so we go left. 23 is less than 25, so we go left. 23 is greater than 21 and we go right. We fall off the tree, so we know that we need to place our new connection right here. And this is what our tree would result in a structure of, following these three insertions in the order provided. Here it is again, if you wanted to see it. It looks the same. Yeah, got nervous, but it looks the same. Okay. So we did notice that the order mattered, and we did talk about why, but you can also see it right here. So in the original order, we end up with like a linear line right here, 15, 16, 17. Whereas over here, we end up with more of like a crooked tree, 15, 17, 16. And this is important. This configuration is important because if this can change, if the order in which we enter our values changes the configuration of the tree, then the order in which we enter our values changes the potential runtime of our algorithm, which we will see shortly. Now, before we get into that, we're going to just look at our delete. And before we break out the deleting from a tree, we have to understand how to find some other important pieces of information. We've done a search, we've done an insert, we've done minimum, we've done maximum. Let's talk about successor. So a successor, the term successor actually means the next value that would appear after some value k in our tree. So given the tree that we have here, if we look at 17, and I asked you, what is the successor to 17? You would see it's 18. That is the next largest value. It is the next number that comes up. So it's not necessarily something that comes down underneath us, but rather has to do with the chronological ordering of the values. So the successor to 6 would be 9. That's the next largest value in our tree. The successor to 32 is 36. The successor to 20 is 21, and there is no successor to 40. So here are some more examples that you can walk through if you're looking for some more practice of what your successors might be. So let's imagine that we're given a pointer to some node n and it contains some value k, and we want to find out which node contains the successor of K. So if we look at 36, I guess, for a second, and so we're given this node N and this value K, and we want to know who is our successor. What are we going to do? Well, we need to find a way to start up here. We need to search and find our node N, and then we need to find our next largest value. So if N has a right child, then the successor is the minimum value of the subtree rooted at the right. So if we remember how we find our minimum value of a given tree, we need to go as left as possible, but we have to do it off of our right child when we're talking about our successor. So we'd go right once, and then we'd go as left as possible. This isn't a great example just because of the tree here, but let's imagine that we were looking for the successor to the value 18. We would go first to our right child, and then we would go as left as possible, and we'd find our successor right here. And that's really the key. We go right if there's a right child, and left as possible after that. And that's sort of our typical easiest case of finding a successor. Now, if N does not have a right child, we have to do something else. We'll have to examine all the nodes on the path from N back toward the root until we reach the first node that is a left child. Its parent node, if any, would contain the successor. So if you know that you're going to need a successor, it's sometimes nice to also keep track of your parent pointer, but it's not necessary because we can use backtracking through recursion as a way to find our parent and our successor as well. So you can do it through implementing sort of like a doubly linked tree where you keep a pointer to who your parent is, but it's not required because if we were looking for the successor to, let's just do the successor to 17 for a second here. We would start up here and we would make our way down with calls on the stack. And we would try to go right and we'd go, oh crap, we don't have a right child. So what are we going to do? We're going to actually make our way exactly what it says here. We're going to examine all the nodes on the path from N, so from 17 back toward the root until we reach the first node that is a left child. Okay, so we're going to go back up and we're going to look for a left child. Is this a left child? It is not a left child. It was a right child. And we come back up here. This is also not a successor to us as well. Oh, a successor to us as well. So we keep backtracking all the way back up until we find our successor. This was where we made that first jump to the left. So this jump to the left is what dictated the fact that this was our successor node. Okay. So let's look at one more where we want to find the successor that is a similar situation. Let's look at 9. For looking for the successor of 9, we would do the same thing. We'd call down our call stack until we found 9. And then we would say, do we have a right child? And we'd realize we don't. So we'd have to backtrack. And as part of our backtracking, we'd go up to here and we'd see, well, we were on the right of that. And so then this here is our first jump when we went to the left, which means that this is going to be our successor. So we do have an algorithmic way of finding our successor, even when we don't have a right child. And we don't need to have parent pointers. Now, this is important because we're going to use this successor algorithm in order to do our deletes. Let's imagine for a second that we wanted to delete a leaf node, because that's our simplest case. If we want to delete a leaf node, it's quite simple. We'd go and find the value. We'd walk down and we would say, is the cur, here, we'll do cur like this. Is cur our value? No, it's not. The value we're looking for is 20, which is bigger. So we'd go to the right. Is 27 our value? No. Then we're going to, and we should probably have a prev as well that keeps following us behind just for our purposes here. Cur is greater than 20, so let's go to the left. Move both those. Cur, we're looking for 20. It's less than 25. We go down here. Cur is less than 21. We go down here. Cur is equal to 20. So we need to grab our prev dot left, since that's the way we walked, and set it to null. And in doing that, sure, cur might still be looking at that, but our actual tree now has a null here. What a nice, easy, simple way to do our delete, right? Since 20 is a leaf node, we can just remove it and it doesn't change anything in our tree structure. Super easy. We just set the left pointer of the parent to null and we're done. That was very straightforward. Let's look at the next case here. Not a terribly complicated case either. If we have an internal node that we are getting, that we're deleting, and our internal node can include our root in this scenario if we only have one child off of them. So an internal node with only one child, what are we going to do? Well, if there's only one child, we just need to not lose our connection, but it works just like a regular linked list. So we would basically walk our way down to this state. And if we walk our way down to this state and we realize that cur does not have a right, but it does have a left, we could say cur's subtree is going to be equal to cur dot left, or sorry, cur dot right, pardon me. And all we need to do is connect our previous's left off of cur, but rather connect it to cur subtree. So prev dot left, because that's where the node that we're getting rid of is, it's on the left, needs to become equal to that cur subtree variable that I just sort of created there. And what that means is this connection will be broken. This connection gets created right here. And then when this method ends, and all these local variables disappear, cur was a local variable. Nothing is looking at 2 anymore. And so garbage collection will see 2 as an orphaned variable and will come and clean it up and it will be gone at that point. So since node has exactly one child, we can just promote its child to take its place. We orphan 2, we hack it off, and we promote its child up one spot. Now, we can't just swap the value, because if you put the value 3 here, there could be more tree that is still a problem. So we don't quite just like swap the values. We do take this link and connect it to 2's child, right? So node 2 is a left child. So we set the left pointer of its parent to point to its child. And that's all there is to it. That one's not so bad either. Now, the trickiest one is slightly different. This is the end of what we just did, right? So we got rid of 2 and now 3 is there. So the trickiest case is our third case, which is when we have 2 children. Oh, I guess we can do one more. Okay, let's just do one more here. Try another one. We want to delete 15. We go to find it. We see it's the left of 12. We see we only have one child. So we connect the left of 12 to its child. And that's all there is to it. So if we'd want to redraw that a little bit nicer, we could do something like 17 and 16 are there. 17 would end up there. And 16 would end up there. There we go. Right, so we found it. We promoted the child. We deleted everything else. Retain our original structure. If our nodes did have parent pointers, we'd also have to update those. But again, this doesn't require parent pointers. You can just use normal recursion. You can use prev and cur. There are ways that don't require you to have a doubly linked list, a doubly linked tree to solve this problem. Okay, I didn't realize where that was going to stop us. So let's just continue with our delete in this video, and then we'll do the traversal in a different video. So case 3 is our internal node has 2 children. So here we're going to try and delete the value 27. And it's not quite as simple as our previous example. So before we were just promoting one of our two children, but now the question is, which of the two children should we be promoting? Do we promote 25? Do we promote 36? What are we going to do here? It becomes a little bit more complicated. And we can't always guarantee that it makes sense to promote one over the other. We need to delete this node without disconnecting anything and maintaining our property that makes a binary search tree a binary search tree. So what can we do? We can use the trick of finding our successor. So we figured out earlier in the video how to find our successor. We call that function, we get the successor, and all we do is swap these values. So our successor just needs us to swap these two values around. 27 ends up there. 32 ends up there. And then it's as simple as deleting a leaf node. We can just axe that leaf node off, and we're maintaining our tree structure. So we're just looking for our successor, and a reminder that it would be the minimum value of its right subtree. So we went right, and then we went as left as we possibly could, and we found it. We did our swap. We removed the leaf, and we're good to go. In this case, our successor has no children, so that's no problem. We were able to just do our swap, and we were good to go. Now, there is other scenarios, as we know, where our successor could have children still attached to it. But in general, the successor node could have a right child, but it's not possible for it to have a left child. So if our successor node does have a right child, we know it's not possible for it to have a left child. Why do we know it's not possible for it to have a left child? Because if there was a left child, that would mean that there's more minimum values to be going to look for. So we know that it's not possible for there to be a left child. It could have had a right child, like it's possible that there would still be like a 33 here, in which case when we do that swap and we put 32 up here and 27 here, we can't just set this to null, but we can quite simply then set this one's pointer to this one's child, because that would just be a deletion with one child. So we're either doing a direct delete of having one if 0 children, we just set the left or right to null, nice and easy. If we have one child, we do that promotion thing where we have to promote everything up, but it's kind of just like a normal linked list delete. You have to make sure you're setting the right left and right nodes, but it's really just like a pretty straightforward delete. Instead of dot next, you're saying dot left or dot right, and on your cur, you're just going to do dot left or dot right. Simple enough. If it's one child, if it's two children, you're going to do that successor, swap, and then 0 or 1 child choice. Just depends on the scenario. That's all there is to it. So it looks a little bit more intimidating than it actually is. So we did our swap with the node to be deleted with its successor node. That's okay that it currently violates, right? This will violate our binary search tree property because now 32 is here. 27 should not be on the right side of 32, but it is. But that's okay because we're going to fix it right away when we finish off this delete of 27, because now we just set it to null. And we're good, because after that swap, the node to be deleted is guaranteed to have at most one child. So we just delete it following case 1 or case 2, as we did previously, and we can fully remove it that way. So in its new location, node 27 is a left child with no children node. We just set the pointer, like 36's left pointer, to null, and now it's gone, and we have successfully deleted 27 from our tree. I will walk through deleting one more, and then I will leave it up to you to delete each of these in the order given to see what happens. So let's start with trying to delete 25. So the first thing we have to do is actually find the node that we wish to delete, which is right here. Once we have found it, we have to assess what case situation it is. We can see that this is a case 1, well, case 2, I suppose, because there's only one child. what do we do in this scenario? We just promote our child. So we would take our 27 and we would take this pointer and just connect it to this child, which would allow us to successfully, I want to like hide that. It would allow us to successfully delete the previous child. There, that looks sort of like what I want it to look like. Odd, but there we go. And so we've successfully deleted 25, and we've rerouted the 27 left child to the 25's child, which was the 21 subtree. Okay, that can be seen right here. Now, I'm not going to show 36, 18, and 20. You're going to go through those on your own whenever you feel like it. The end result is also in these slides as I skip past them. Okay, so we've now done search, insert, and delete into binary search trees. Join me in the next video where we're going to talk about tree traversals and how to go through them, as well as algorithmic analysis to sort of wrap up this binary search tree topic. Thanks, everyone, and have a great rest of your day.